In the vast expanse of space exist remnants of dead stars. These are not your average stellar corpses. These are neutron stars, objects so dense they boggle the mind. Imagine the mass of our sun squeezed into a sphere the size of a city. That's a neutron star. They are the densest objects in the universe except for black holes. Neutron stars challenge our understanding of physics. Their interiors are composed almost entirely of neutrons, subatomic particles packed together incredibly tightly. These bizarre objects are more than just curiosities. They are cosmic laboratories offering insights into the fundamental laws of nature. Studying neutron stars allows us to probe matter under extreme conditions that we can never replicate on Earth. Their intense gravity warps space-time, creating environments where time itself flows differently. Neutron stars are a testament to the universe's ability to create objects of unimaginable power and strangeness. Neutron stars are born from violence. They are the remnants of massive stars much larger than our sun that have reached the end of their lives. These stars burn through their nuclear fuel at furious rates, eventually exhausting the supply that keeps them shining. When that happens, gravity wins. The star's core collapses in on itself, triggering a catastrophic explosion, a supernova. Supernovae are among the most energetic events in the universe. They can outshine entire galaxies for a brief period. During the explosion, the star's outer layers are blasted into space. The core, however, undergoes a remarkable transformation. The intense pressure forces protons and electrons to combine, forming neutrons. This process gives birth to a neutron star. The newborn neutron star inherits the rapid spin of its parent star. It also possesses an incredibly strong magnetic field, trillions of times more powerful than Earth's. These characteristics contribute to the unique properties of different types of neutron stars. The density of a neutron star is almost impossible to grasp. Imagine taking Mount Everest, the tallest mountain on Earth, and compressing it into a teaspoon. That's roughly the density of a neutron star. A single teaspoonful of neutron star material would weigh billions of tons on Earth. This extreme density is a result of the crushing force of gravity. The gravitational pull on a neutron star is millions of times stronger than Earth's. If you could stand on the surface of a neutron star, you would be instantly flattened. The difference in gravity between your head and your toes would be enough to rip you apart. Light itself is bent by the intense gravity of a neutron star. This effect, called gravitational lensing, allows us to observe the region behind a neutron star as light is warped around its edges. Even more astounding, the intense gravity of a neutron star slows down time. Time passes slower on the surface of a neutron star than it does on Earth, a phenomenon known as time dilation. Not all neutron stars are created equal. Some emit beams of radio waves from their magnetic poles like cosmic lighthouses. These are called pulsars. As a pulsar spins, its beams sweep across space. If Earth happens to be in the path of a beam, we detect a pulse of radio waves, hence the name Pulsar. Other neutron stars, called magnetars, possess even more extreme magnetic fields. These fields are so strong that they can distort the shape of atoms. Magnetars release enormous bursts of energy, known as giant flares, which can be detected across vast distances. These flares are thought to be caused by sudden shifts in the magnetar's magnetic field. Pulsars and magnetars provide us with valuable insights into the extreme physics at play within neutron stars. Their rapid rotation and powerful magnetic fields make them natural laboratories for studying fundamental forces and particles. Observing these objects helps us refine our understanding of the universe's most extreme environments. The extreme nature of neutron stars has led to some intriguing speculation. Could advanced alien civilizations harness the immense energy of these objects? Some scientists believe it's possible. A hypothetical structure called a Dyson sphere, built around a neutron star, could capture a significant portion of its energy output. While this is purely speculative, it highlights the fascination neutron stars hold. They are cosmic powerhouses dwarfing our own sun in terms of density and gravitational pull. Their unique properties could potentially be exploited by civilizations far more advanced than our own. The possibility of alien life is a topic that has captivated humanity for centuries. Neutron stars, with their extreme environments and potential as energy sources, add a new layer to this ongoing mystery. While we have no evidence of such civilizations, the vastness of the universe leaves room for endless possibilities. When two neutron stars collide, the result is a cataclysmic event that sends ripples through space-time. These collisions are among the most violent and energetic events in the universe. They release more energy in a few milliseconds than our sun will emit in its entire lifetime. These collisions create a spectacular light show, known as a kilonova, that can be detected across billions of light-years. But more importantly, they are responsible for creating some of the heaviest elements in the universe, such as gold, platinum, and uranium. These elements are forged in the intense heat and pressure of the collision and blasted out into space. The gold in your jewelry, the platinum in your catalytic converter, and the uranium used in nuclear power plants, they all originated from these cosmic collisions billions of years ago. Neutron star collisions are essential for enriching the universe with heavy elements, the building blocks of planets and life itself. While we've learned much about neutron stars, their cores remain a mystery. The pressure and density at the core are so extreme that they defy our current understanding of physics. Some scientists speculate that the core might contain exotic forms of matter, such as quark matter or strange matter. Quark matter is thought to be composed of quarks, the fundamental particles that make up protons and neutrons. Strange matter, even more exotic, is hypothesized to be composed of strange quarks, a type of quark not found in ordinary matter. If these forms of matter exist, they could hold the key to unlocking new realms of physics. The study of neutron star cores is a frontier of science where our current knowledge meets the unknown. Unraveling the secrets of these extreme environments could revolutionize our understanding of the universe's fundamental building blocks and the forces that govern them. Neutron stars are more than just fascinating objects. They are cosmic beacons, providing us with invaluable information about the universe. Their extreme density and gravity allow us to test Einstein's theory of general relativity in ways not possible on Earth. Pulsars, with their precise timing, act as cosmic clocks. By studying slight variations in their pulses, astronomers can detect gravitational waves, ripples in space-time caused by some of the most violent events in the universe. Neutron star collisions, meanwhile, provide clues about the origin of heavy elements and the conditions in the early universe. Neutron stars, these stellar ghosts, continue to captivate our imaginations. They are reminders of the universe's immense power and the mysteries that still abound. As we continue to study these objects, we will undoubtedly make even more profound discoveries, deepening our understanding of the cosmos and our place within it.